So let's talk about the gas laws, right? Speaking of equations of state, right? So we know Boyle's law, and Boyle's law says P times V equals a constant at constant number of moles N and temperature T. Okay? Charles' law says V over T equals a constant at constant N and P, okay, constant number of moles and pressure. And then Avogadro's principle says V over N equals a constant at constant P and T. Okay, so now what do all of these mean? Well, we could rearrange this, right, algebraically, and we know really Boyle's law says that P is proportional to 1 over V, of course at constant T. Okay, so Charles' law says V is directly proportional to T at constant N and P. And of course, Avogadro's principle says volume or number of moles are directly proportional to each other as well. So here in Boyle's law, right, as the pressure goes up, the volume has to go down. Or as the volume goes up, the pressure has to go down. They're inversely proportional. But Charles' law, right, volume and temperature are directly proportional. So assuming that number of moles and pressure are held constant, if you increase the temperature, you increase the volume. You decrease the volume, you decrease the temperature. And similarly with the Avogadro's principle, assuming pressure and temperature are constant, then if you increase the number of moles, you have to increase the volume. And so now here we have our total equation of state, the ideal gas law, the combined law, which of course we know is P is a function of V, T, and N, which equals nRT over V. So the gas constant, R, is this constant of proportionality that allows us to combine all these laws. And really, it's not the gas constant, right? It's Boltzmann's constant. But you knew that, okay? So Boltzmann's constant is what allows us to combine all of these laws. And so now here is a capture from your book, from Atkins. And I think this is pretty cool to see this gas law on this three-dimensional landscape, okay, P, V, and T. And we can actually point out the individual laws from this landscape. So for example, if we see PV equals a constant, here it is, right? Okay, so here is our Boyle's law, okay? And so that's P inversely proportional to V. So imagine this shape, right? Imagine how this looks on the three-dimensional graph. Imagine how that would look on a two-dimensional graph, right? So now Charles' law is V and T are proportionate. And so, by the way, sorry, Boyle's law gives us an isotherm. Iso meaning the same, isotherm, so temperature is constant. And we can see on this line, right, this is a line of constant temperature. Charles' laws gives us an isobar. So that's a line of constant pressure. And here you can see it's kind of tough because it's not on an axis that we're used to seeing. But if I were to take this three-dimensional graph and flip it up like this, right, so that I would have, let me see if I can even do that, a volume on the y and temperature on the x, then, right, we would see this constant proportionality. Whereas, right, Boyle's law, P over V, does this inverse relationship, okay? And then finally, the Avogadro's principle gives us, let's see here. It's actually, oh, Charles' law also, sorry, I didn't point out. If we fixed volume in Charles' law, then we also know P is directly proportional to T, assuming V is constant. Sorry, this is getting a little sloppy. So this, where did it go? This PT, this isocore, that's also a manifestation of Charles' law, okay? And so you can see at constant volume, pressure and temperature will increase directly. So two lie in some Charles law, isocores as well as isobars. Okay? And because we don't have a number of mole access on this, the entire thing is really directly related to Avogadro's principle, because Avogadro's principle is what allows us to put together these laws, in addition to, of course, the Boltzmann's constant of proportionality. Okay, so now I'm going to move on, and we're